And now we're continuing with a topic what I always find very important, giving the floor to our young professionals. We do that with the poster sessions, we do that from time to time in breakout sessions, and we do this every year with the Thesis Award. So I'm going to hand over the microphone to the chair of the jury and give it now all in your hands. Ricardo.
Okay, good afternoon. I'm still recuperating a little bit from the former presentation, but so it's a great pleasure for me to be the chair of the jury of the Thesis Awards. In the former years, our colleague Paul Verlaan, a former fire chief who was the most scientific fire chief of the Netherlands, always was the chair of the jury, and now he passed on this task to me. I have been a member of the jury for a few years, and it was a pleasure always to read all these theses and be in that jury. And it is a great pleasure, but also very important. René already said it. This conference is about the connection between science and practice. And that's why we need universities to cooperate with fire services to strengthen our profession. That's also why we are happy that so many speakers, presenters, and also students are here from universities from Edinburgh, Lund, Ghent, but also from our own universities, Twente, Eindhoven, and also institutions for higher education. So we are very happy that students are still interested in our profession, because that is important. And we could see it, for example, from Ruben. Now I know how to tell everybody that investment in prevention pays off. So, and nobody would believe that, because but now we have very good arguments to underpin this, and that's why we need to invest in students. And I'm very happy that that we had for this Thesis Awards, in which we cooperate the Association of Fire Prevention Advisors from the Netherlands, the VVBA, and the IFV cooperate already for 8 years to do this Thesis Awards. And this year we had 11 theses to judge. The first selection was made by the members of the Association of Fire Prevention Advisors. There were 11, and there were 3 nominations. The jury, by the way, from these 3 nominations, the jury consists of Ruud van Herpen, Lieve de Witte, where is he? He went. Oh, over there, yes, Lieve de Witte, and myself. So we had a 3-person jury for the final selection of the 3. And of course we are going to announce the winner, but we are not going to announce the winner before you also did the presentation. So it is not that easy for you. But it will be going okay. And you have exactly 10 minutes, so I'm going to be very strict on that. Is the order? No, there is no order, so I can determine the order. And we have, first of all, we have Farah Forzi, and she is from the University of Edinburgh. She will do the first presentation. Wait a minute, and it will be about flame propagation between flat roofing and photovoltaic installations. And the second presentation is from the Netherlands. It is, I can say Tineke, Tineke School. And she's from the University of Twente. And she made a log Gaussian-Cox process for predicting chimney fires in the fire department of Twente. And she's going to explain to us what is that log Gaussian-Cox process. I already read it, so I'm... And then the third one is Sohila Bigdeli, and she is from the University of Ghent, and she did a CFD modeling of medium and large scale fire plumes, and I think that the fire safety engineers amongst us will recognize this, but she's going to explain to everybody what does it mean. So the first, Farah, I invite you to stand up and do your presentation. I wish you a lot of success. You can use the microphone if you want, or you can do over there. Yes, you want to? Oh, okay.
Is there a...
Lots of success. 10 minutes. Yeah, and I will give you signal after. 8 minutes.
Okay. Hi everyone, I'm Farah Fauzi and I recently graduated from the International Masters of Fire Safety Engineering, which is a collaboration between Ghent University, Lund University and University of Edinburgh. So I'm really honored and excited and slightly is understatement, nervous about presenting my thesis, my master's thesis on flame propagation between flat roofing and photovoltaic installations. So why is this a topic of concern? Basically, solar power generation has been increasing exponentially over the past decade. And this is mainly driven by a need for more sustainable yet financially viable energy sources. In particular, large corporations with large warehouses and factories are increasingly interested in optimizing their large roof areas with rooftop PV systems. However, global occurrences of fires involving such systems raises concern on the inherent hazards involving such installations. And rooftop PV system not only introduces a source of ignition onto the roof, but it also changes the dynamics of a roof fire. So a change fire dynamics on the roof has an impact on fire spread along the roof, and this has a knock-on effect on the potential damage caused. Previous large-scale experiments focusing on this problem has shown that mainly fire spread is confined to the area beneath the panels. So therefore, my thesis is focused on the gap, and in particular the gap height formed between the panels as well as the roof, and how it affects fire spread. So we have a typical roof fire, but the physical presence of the PV module, according to past research, has shown that it leads to an increased radiative heat flux and therefore heats up the roofing material. However, there's a lack of understanding about how this effect is affected by the gap formed between the two surfaces, and how this also affects the rate of flame spread. So this is quite a complex system, and what we try to do is try to simplify the problem to focus mainly on the effects of the gap. So to do that, there's a variety of materials used for PV modules as well as roofing material, and it's important that we decouple the effects of these material properties in order to have a fundamental understanding of fire spread within this gap. So combustible surface is used as a surrogate material for the roof. And we've chosen PMMA not because it's used on roofs. It's not used on roofs, and please do not use it on roofs because it's combustible. And PMMA is selected because it is a well-defined material, which is commonly used in fire spread experiments, and it has a reproducible fire spread behavior. At the same time, previous studies have also shown that PV modules itself have a limited combustibility, which is limited to the backsheet material. So we've used a non-combustible surface as a surrogate for the PV modules. And stainless steel is used just so that it does not introduce undefined fire load into the system. We also done experiments replacing the stainless steel with actual PV panels to see whether the results are reproducible. At the same time, as you can see, there's various angles of inclination of the PV panels on roof. So in order to simplify the problem, we only look at a panel which is horizontal. So with that concept, the following experimental setup was designed. So we have the stainless steel panel, which we'll also replace it with PV panels. PMA sample. We have a lab jack to vary the gap distance between 10 to 25 centimeters. A video camera which is used to monitor the progress of the flame, as well as thermocouples and heat flux gauge embedded within the PMA sample, because we know that these are contributing factors to fire spread. So homogeneous linear ignition is achieved by igniting a strip of ceramic paper which has been laced with methanol. So these are the results which we get where we recorded the progress of the flame front every 50 millimeters. To help you visualize that, we will study mainly on the three situations without the panel at 20 centimeters and panel at 17 centimeters. So if you see these three pictures here, it shows how the fire looks like at 50 millimeters for first 50 millimeters, and you can see that there's not much difference between the three, but you notice a difference when we allow the flame to progress along the sample. So for situations with the panel, the flame spread rate is actually higher and the fire size is larger. But for the 17 centimeters scenario, the fire continues to grow until it impinges on the panel, and the flame accelerates to a resultant flame spread rate, which is around 10 times more than a free burning situation. However, if you see the situation at gap heights of 20 centimeters, the flame spread rate is slightly faster than the free burning scenario, but it's relatively constant and stable. So it shows that the panels at these heights has limited effect on the flame spread rate. This result shows that there's a critical gap height below which a fire may seem small at the start, but if given sufficient time to grow, it will lead to a rapid transition to a really fast flame spread rate, and could result in an uncontrollable fire and increase the damage caused. In order to explain this, phenomenon, we'll also look at the radiative heat flux recorded as the flame progresses. So in a free burning scenario, flame spread rate is mainly driven by the radiation from the flames. At gap heights larger than the critical gap height, the presence of the panel actually forms a layer of hot gas which in turn heats up the panel. And both the hot gas and the panel impose a larger heat flux back to the surface. However, the combined effects is limited in terms of intensity as well as extent from the flame front. However, when the flames deflect, it increases the heat flux directed back to the surface significantly, because now the flames are the ones which are radiating heat back to the surface. And these results shows that the amount of radiative heat flux caused by the deflected flame will actually increase the flame spread rate drastically. Similar results also shown for the temperature measurements. So at the start, for all three scenarios, the temperature profile is the same for all three. This is before flame impingement. There has slightly larger preheated length for the conditions with the panel, but mainly it's limited to a small area in front of flame front. However, when the flame impinges, the temperature gradient near the flame front becomes shorter, and you can see that there's a larger preheated length with a higher temperature in front of flame front. We also did a comparison study together with using PV panels instead of the surrogate material, and we see that there's not much difference, which is good. However, using the PV panels will cause, especially when the flame deflect under the panel, it will cause the panels to disintegrate. And at the same time, when you want to do this for further studies, you need to keep replacing the PV panels. So in this case, using a surrogate will be sufficient to give us an indication of the critical gap height. So in conclusion, our results show that just a minimal difference in the gap heights will cause a large difference in the flame spread behavior. So there's a presence of the critical gap distance, which could be used as a mitigation measure to limit the spread of fire. And currently, the gap heights are determined in building design by architectural interest, seismic considerations, or wind load considerations. And this might act to try to reduce the gap heights, but this contradicts to what is needed in a fire safety point of view. So with this study, we hope to be able to get a critical gap height for PV installations that, that could be a cost optimization measure in the design of PV panels on roofs. However, it would be nice to stand here and tell you what is the gap height which we should be designing our PV panels to, but I can't because this is just a preliminary study. There's potential for this setup and for this setup to continue to be further analyzed and further refined in order to get more useful data. However, I'm quite happy that, like, all hope is not lost, because I'm quite happy my thesis will not be sitting in a library and collecting dust, because it's part of a larger research project led by two people who I've yet to introduce, and that's my supervisor, Professor Gunder Jomas from the University of Edinburgh, and his PhD student, Jens Timon Christensen, who is here today, and giving a workshop later, so if you have any further questions, please ask him. Yeah.
Well, thank you very much, Farah. You were exactly within the 10 minutes, so congratulations. And I forgot to tell you before, but the students also produced a very beautiful poster, which is in the poster session room. So if you want to know more about this, then you can read it over there, because there is no time to ask questions at this moment. So then the second one is Martine School, of Tineke School, mag ik zeggen. So it's okay, the floor is yours, and please tell us about these difficult names.
Yes, I will. So, hello everybody. I graduated last year as an applied mathematician, and I did my research at the Fire Department Twente. Yeah, the first slide is in Dutch, but the rest of the presentation is in English. Just a little mistake from me. The simple title is: we predict chimney fires with the help of mathematical models. Yes, at the Fire Department Twente, they already collected a lot of data on the fires and accidents that they had to cope with from 2005 until 2017. And they wanted to do something with this. They wanted to predict fires, actually, because that's quite a difficult subject. We choose to focus on chimney fires. This is because chimney fires are the largest type of fire in Twente. We see them on the right. From 2005 until 2015, chimney fires had happened in all these places in Twente. We see the cities quite good, but also outside the cities, chimney fires have happened. And to build a predictive model, we want to find a pattern between the data of chimney fires and data that we have available. For my thesis, I combined two models, a correlation model and a noise model. This correlation model finds this pattern between spatial and temporal variables and chimney fires, and this noise model can add some randomness to this model, so that the total model is the combination of those. So first, the correlation analysis. We are using an inhomogeneous Poisson process for this part. Just a name. Yes, and we want to check which spatial and which temporal variables have an influence on chimney fires. For spatial variables, you can think of how Twente looks like, so where the number of buildings, number of older buildings, number of residents, etc. And for temporal variables, you can think of weather conditions, or maybe on a holiday we expect more chimney fires, things like this. To do this comparison, for the spatial variables, we divided Twente into boxes from 500 by 500 meter, and we compared the data for this 500 by 500 meter box with the number of chimney fires that we have in our data. For temporal variables, we did kind of the same thing, but then we divided the data into days. One very important data that we wanted to have and to include is the number of chimneys in Twente per box, but we didn't have this data available. So what we wanted to do is to estimate this number, and we tested for that 4 different spatial variables. I listed them here: the number of freestanding and townhouses or 2-in-a-row houses, the number of old buildings, the total number of buildings, and the amount of residents. These all could estimate in some way the number of chimneys. So that's why we included them. For the correlation analysis, I tested 35 variables, and the top 10 is listed here. Here we see 2 temporal variables on top. This is the daily mean temperature and the daily mean wind chill. They both have a very large correlation coefficient, and that's why we want to include them in the model. The mathematical model needs to have independent variables, and therefore we only include the top one in our model. This is the daily mean temperature. And then the first spatial variable that we see here is the number of residents, and we wanted to include this as well. To include these variables, we need to fit an intensity function. I tried 3 different types of intensity functions to fit to the data. And here we have the results of that. So on the left, we have the number of residents per box, from low to higher, and the mean amount of chimney fires. We see that at first we see an increase in the chance of the occurrence of a chimney fire, just because there are more people, more houses, more chimneys. After a certain point, it decreases again, and we can explain it by saying when a large amount of people is living there, we see a lot of apartments which don't have chimneys. Quite logical. So the best fitting function here we included in our model. On the right picture you see simply the lower the temperature, the higher the chance of a chimney fire. These intensity functions can form already a model, and we made predictions with that, but then we found that there was still something missing. And we found that this was because of the weather tipping point. Especially in October, we predicted much less events than actually happening. And this is, we thought that this was because of, in October, the temperature drops below a certain point. People start making fires in their houses. The chimneys are not cleaned, they're maybe dirty, just not used enough. And therefore, the chance of the occurrence of a chimney fire is simply higher. We wanted to include this as well. So our inhomogeneous Poisson process, the correlation model looks then like this. We have 3 intensity functions for the number of residents, the temperature, and October. Okay. And to add this noise model, so the first model can predict around 85% of the chimney fires. And to make the model simple, like this, we want to add a noise model, which is simply a random field which fills up these gaps. You can see it like this. With that, we can make predictions, and I have results of that. So as I said, I built a model on data from 2005 and 2015, and here 2016 and 2017 are listed to show the results, to validate. On the left, we have we predicted per week. So we have here the week numbers. The red dots are the predictions, the crosses are reality, and the blue area is the confidence interval, which follows from a mathematical model. We see that actually 85% we are inside the confidence interval, which is quite good. We see some outliers in the summer, which is still difficult to predict. There's one or there's none. And in October, it's difficult there. In October, it's still quite difficult, and at the end of the winter as well. But still, these results were quite satisfying, and that's why the fire department asked me to build a dashboard for it, to make the model also usable for the fire department. That is this. This dashboard has as input the temperature forecast and the spatial variables, which are for the number of residents in Twente, and also the October variables included here. On the left, we have a map which shows the chance of a chimney fire within these 500 by 500 meter boxes. On the right, it's listed per area which has the highest chance. Also the areas with the highest chance, the days with the highest chance, the confidence interval, and then the final prediction on the right below. Yeah, because chimney fires, it's a type of fire, and it's actually occurring quite a lot in Twente, but there are still hundreds of other types. So in the future, they would like to extend this and use the same models for other types and combine them, and hopefully in the future we then have a predictive model where the firemen can, use. Yeah, thank you for your attention.
Well, thank you, Tineke. You were well within the time, so there is some time to relax now, yes, because there was a lot of commotion in the conference room. So, last one, Suhaila, may I invite you to do your presentation?
Okay, thank you. So, good afternoon, everyone. I hope you still have enough energy for 10 more minutes before lunch to listen. I'm Suhaila, fresh graduate from Fire Safety Engineering from Ghent University. I'm working for Fire Engineering Solutions Ghent company, and I will present the results for CFD modeling of medium large-scale fire plumes. The content of the presentation introduction. I will talk about the goals and the study steps and the test cases that we studied and the final conclusion. Why did we choose to do fire plume modeling? In fact, it's a basis for so many complicated other scenarios. Like if you want to simulate how a sprinkler effect is in your model, at first you need to have a precise modeling of your fire. So we wanted to go for the fire plume modeling, but you can see this really complicated phenomena, and so many phenomena are involved, and if you want to model it, it even becomes more complicated. So models are involved, so model constants are required, so it is quite a job for users to apply the model and use them. So the solution is that to move toward predictive fire modeling, where we propose a tool, we give models which require less user adjustments so that we make the job easier for the users. And of course, we want to have models which have a wide range of applicabilities. So the goal is to have predictive fire modeling. We validated and evaluated Firefoam software 2.2.x, and of course, in my thesis, I didn't have enough time to look into different models that are involved in a fire case. So we looked into turbulence, combustion, and radiation. So we started with a simplified case, non-reacting case, helium plume. We checked the turbulence model, and we figured out what is the best model there. And then in the next step, we added complexity of combustion modeling. And we also tried to use the turbulence model from previous step. So can we again model another test case with this model? And again, one more step toward predictive modeling, we added radiation, and again, using all the results from previous steps in another test case. So, the first step, Sandia Hel Plume. I'm not gonna go too much to details about the experimental test case, but it's just simply, as you can see in the picture, it's a 1 meter diameter inlet with which helium is injected into the compartment, and it generates buoyancy-generated turbulence, which nicely resembles fire plume behaviors. So here I'm just showing the computational domain that I used in my simulation, and I did mesh sensitivity analysis. We were on the case for 35 seconds, and we had variable time step sizes controlled by maximum current number of 0.9. I will show you now some results, this is the inlet, 20 centimeter above the inlet.
different turbulent model that we applied and we use in our simulations. You can see the graphs for average helium mass fractions at different cell sizes. What I would like you to notice in this slide is that to see the difference between these already available Smagorinsky one-eddy equation model, already available models within the software with their theoretical constant, 0.094 and so on, compared to the, the dynamic models that we applied into the model. You can see how grid sensitive are these models. So with these dynamic models, you can, go to rather relatively coarse cell sizes. So it helps a lot. And we also wanted to see, okay, is it possible to, get the good results if we modify the model constant for these static already available models? Yes, it is possible. We changed the model constant, you can see there. And but it required us to do extra simulations. It is not predictive fire modeling. It means we have to do, extra simulations, and sometimes it's not just you will get the results after only one extra simulation. So these dynamic models, which give you, nice results, not that much mesh sensitive, they're there. You can use them without needing to adjust any constant and so on. So I didn't show you so much of the simulation results that we obtained. We also checked the numerical schemes and their effects. So what I would like to show in this slide is that to notice that what would be the simulation uncertainty if you include only, depending on the choice of your turbulence model and a numerical scheme. It can be like this much if you're in a coarse mesh, and the uncertainty reduces as you go to finer mesh size, simply because you're resolving more flow structures, and in fact you're reducing the impact of your model. So next step, combustion modeling. We took McCaffrey test case results. It's a natural gas 30 centimeter by 30 centimeter burner at different fire loads from 14 to 57 kilowatts. So here I'm showing the computational domain. We also adjusted the inlet mass flow rate to have the same fire loads, and yeah. We tried the two different models, eddy dissipation model available in the software, eddy dissipation concept that we already applied it in the model. You can see that how these combustion models and also turbulence models, the dynamic models that we applied in these cases, can nicely, reproduce the experimental results. So all the simulation results for different heat release rates, all of them collapse onto each other as in the experiments. We didn't see too much difference between these two models. It's simply because we didn't, introduce the possibility of having dissociative and intermediate reactions, which is possible to have it in the eddy dissipation concept. That could have made higher, differences between these two models. But in total, with all the results that I'm not showing here, we found that we get closer results to experiments if we use eddy dissipation concept model. So, because it incorporates, turbulence and combustion modeling into your model. This is what we would like to see. So, this is the best model for combustion modeling we figured out in this case. Another test case that we simulated, and we wanted to see what would be the best radiation model. It's a methanol 30 centimeter burner diameter and 1 meter above the floor. Unfortunately, I didn't have enough time to go for mesh sensitivity. That's why, again, because of time limitation, I went for rather coarse cell sizes. That's why you can see here this weighted sum of gray gas model is the model that we applied, and constant radiative fraction is the already available model there. So you can see that the results are not very close to the experiments, but they're still good. But I don't want to explain, you know, the results here. Just I want to stress the fact that with constant radiative fraction, it is true that you can have similar results compared to weighted sum of gray gas model. But in fact, you have to have good experimental data that tells you, okay, what is the radiation fraction? That then you have the data to put it in your model. But with weighted sum of gray gas model, you don't need that. The model itself will calculate dynamically the radiation fraction for you. And this is one step more toward predictive fire modeling. So here is the weighted sum of gray gas model is the best. So the best models for predictive fire modeling are the dynamic Smagorinsky with variable Schmidt number, eddy dissipation concept, weighted sum of gray gas model. No tuning was required, but have in mind, this conclusion only applies to my simulated test cases. So for your own specific test case, please don't rely on me, do your job. And yeah, and predictive fire modeling is good, but it's costly. So it depends on you. Do you want to spend extra time on it? Thanks.
No. Thank you very much, Suhaila. Is there anyone that wants to volunteer to be in the jury next year? Because you can imagine what Ruud Lieve and I were going through reading these beautiful theses of yours and also the very interesting subjects that you proposed to us. And well, it was really, of course, every jury says it, that it is really difficult to choose which is the best one because the subjects are a little bit different. And also, I must say that we think that all these theses were of high level academic and scientific level. So we could not choose between the scientific level or the subject or the methodology, because everything was almost perfect. So in that sense, your thesis did not discriminate. So what we thought was, of course, the purpose of our thesis award is that it should be practical, it should be innovative, and it should be also striking, yes, for the people that read it. And some of your theses were very difficult for outsiders, were really meant for insiders. So that is what we also took into account, and then we were able to make a choice. First of all, first the jury report. It was like before I'm going to announce who won. First, Farah. So we think that the strong points of your thesis was that it is a current and relevant subject. You could hear it in the conference room. A lot of people recognize the problem. It has a clear vision and a problem definition, and we thought that your thesis was the readability of your thesis was very good, so everybody could understand what was written. Less strong was maybe that you only used only one experimental method. Yes, it was only experimentally and there was no calculation. So that could have been a little bit better. So, and we thought it was a less innovative and applicable. But it is a very interesting subject, and it is a step ahead in understanding what we can do to prevent fires involving photovoltaic cells. A real fire safety engineering thesis was our conclusion. And then Martina. We think it was a very interesting thing to see how you can apply mathematics to a problem for the fire service. So in that sense, it was interesting and also innovative to do it in this way. And we think that for the fire services, it is also innovative to use data and to try to predict fires. It is a part of business intelligence, an innovative way of firefighting. On the other hand, your thesis was really very difficult to understand because there were a lot of formulas, and you saved a lot of formulas in your presentation. You showed them a little bit, and we think that for insiders it is really great, but for outsiders to read, maybe a little bit more difficult. And we think there should have been a little bit more attention to explain for outsiders what is meant with all these methods and difficult processes, Poisson processes, etc. But still, of course, very interesting and a very nice subject, and also the result with that dashboard is very interesting. Then, last one, Sohila. Well, I think it was the most difficult thesis that we think it is very important for people that do CFD simulations, because it is a step ahead in understanding how to simulate this kind of situations. It was a high scientific level and it gains insight. And we think it is a next step ahead, so like I said. But it was, on the other hand, also very difficult to read for outsiders. This really meant for insiders to read and to understand. And we think the innovativity and the applicability at the moment is still rather limited. So this is the jury report. I want to ask you to come forward, because I think it is great that you were nominated, and that is already a little bit of winning. So please come forward and have a big applause for our three. Because, of course, we have flowers for all of you. Yes? That's how we start. And I want to congratulate you with the nominations. Yes? Farah, congratulations. And Tineke, congratulations with your... Oh. And also for Sohila. And I think it is great of the three of you that you were here and present your difficult thesis in a very understandable way. So, and of course then, that's the moment where all of us are waiting for. The jury decided that the thesis of Farah was the thesis that should win. So, congratulations. It was, you remember it was about the photovoltaic cells, yes? Okay, and we have a prize, yes. Okay, so, because I forgot to tell that the winner gets a prize of 1,200 euros to spend for a subject of FSS importance, yes? Congratulations with your prize. So, and I think we have to make... Oh, yeah.
No, it's okay. It's okay.
I have to make a picture. So, and of course, I hope you are not too disappointed, because you did a great job today here, and also congratulations. And we have to fill in your name. We will do that later on, okay. Because do we do it now? Okay, yeah, we have to fill in your name. But then, can you help me then? Dan moet ik wel die naam hebben.
Ja. Oh.
It's my first time. I can understand. And your flowers. So, this was my item, and I give the word to René.
Yeah, Ricardo, thank you. And thanks do for me, 3 winners. Okay, too short. Yeah, you may stay there, no problem for me. Two short messages before we go for lunch. The first one is in the program, what maybe you picked up this morning at the entrance, states that in the afternoon there's only one breakout session with Michael Reich about smoke stopper. that's not true. It's just 2. So if you signed in for the first one and your bets is correct, you just can go in for the first session with Michael for when you signed in or want to come in, because it's just normally 2 sessions. Yeah, that's the one thing I want to say. And the second thing I want to say, yeah, I'm glad I forgot the date. The next FSS conference is not in 1 year. For the first time, it's 1 year. We're going to 1.5 years now. And I don't want to say we will do it every 1.5 years from now on. But we see with so many people from abroad that it's a pity that it's in November, because you're coming in the morning when it's dark here in the conference room, and you leave the conference room when it's still dark. And in summertime we have some more time. We have marvelous nature here. We have the open air museum, so we can do some more and not only staying here inside for the evening program and so. And on the other hand, 1.5 years give us some time, because it's always difficult to prepare, not the preparations, but to have more than 20 speakers with interesting topics. And we want to still provide you with that. So in your agenda, the 13th FSS conference will be on the 2nd and the 3rd of June. And I know Patrick is very happy with that, because November is always the time that you have your college and your students, and the same goes for the other professors. So we are trying for the first time in June to get Professor Patrick van Hees from Lund, Professor Bart Mercier from Ghent, and Professor Luke Bisbee from Edinburgh, to have them all together at one time here. And that's really where we're going to work on. It's a promise? The first one we have, now the other 2. Okay, have your lunch, go to the breakout sessions, and we see each other this afternoon. Thank you.